Hello, my name is Ben Marshall. I work for ExxonMobil, and the title of my talk is the thermodynamic perturbation theory for sterically hindered hydrogen bonding fluids. The ultimate goal of this work is to develop an equation of state for hydrogen bonding fluids, which includes additional physics as compared to the literature equations of state. And specifically, what we mean is the statistical associating fluid theory class of equations of state, which is our best molecular theory as an engineering equation of state. And the accuracy of staff approaches results from the proper accounting of various size and energy scales. What I mean by that, if we look at propanol, for instance, if you look at cubic equations of state, SRK, Ping-Robinson are all empirical modifications of van der Waals, and van der Waals assumes that all molecules are spheres with a single attractive energy scale. But that's not a good representation of propanol because propanol is elongated, so it has two size degrees of freedom. And also it has more than dispersion interactions. It also has long-range polar and hydrogen bonding interactions. Now the SAF equations of state do a better job of recognizing these various features. And in these approaches, you actually realize that the molecule is elongated. So it's treated as a chain of spheres instead of a single sphere. And also you have multiple energy scales of interaction. You have dispersion interactions, hydrogen bonding, et cetera. The hydrogen bonding contributions to the theory are all treated in Wertheim's first order perturbation theory, and that's what we're going to be talking about today. In the 1970s and 80s, there was a lot of effort to try to develop cluster expansions for hydrogen bonding fluids. This was very difficult due to the fact that hydrogen bonding is a very strong interaction, which means it's difficult to evaluate in perturbation theories, and it's highly directional. And this directionality leads to a limited valence. And the limited valence is the extremely difficult part. And limited valence means that the interaction can saturate with a single interaction. And this is the difficult part, which is to include in a general reformulation of statistical mechanics. Wertheim developed a multi-density form of statistical mechanics, which solves this problem. And in his multi-density form, each hydrogen bonding state of a molecule is assigned its own species density, and then he was able to topologically reduce a cluster expansion and attain a reformulation of statistical mechanics, which incorporates all these basic features of hydrogen bonding. Around the same time, Walter Chapman applied Wertheim's approach within first order perturbation theory to obtain a general solution for an arbitrary fluid with an arbitrary number of components, and each component could have an arbitrary number and type of association sites. And he was able to attain this general elegant solution in first order perturbation theory, and it is this solution which provides the basis of the hydrogen bonding term in the SAF equation of state. Now, the generality of the TPT1 result is obtainable because it assumes that within TPT1, you assume that each hydrogen bond does not interact with other hydrogen bonds on the molecule. So if each hydrogen bond is treated independently, then you can include second order effects like steric hindrance between hydrogen bonding sites, and also, for instance, no multiple bonding of single hydrogen bonding sites. For steric hindrance, we can see an illustration here where molecule 3, ethanol molecule 3, to where we're modeling ethanol here, to where ethanol has two hydrogen bond acceptor sites, O1 and O2, and a hydrogen bond donor site, which we represent as this coarse-grained representation where the two blue spheres represent the hydrogen bond acceptor sites, and the red sphere is the hydrogen bond donor sites, so the hydrogen. So this molecule is bonded at both hydrogen bond acceptor sites to different molecules, so the hydrogens on different ethanol molecules. And in first order perturbation theory, these two molecules don't know about each other. So there are configurations that the theory allows for to where these molecules actually overlap. And this is what happens when you don't account for steric hindrance. But the beauty of the first order approach is that it allows for a simple partitioning of the hydrogen bonding theory. So what I mean by that is if you've worked with SAF very much, you're very familiar with these fraction of unbonded sites, XA, to where XA is a fraction of sites of type A on a molecule which are not bonded. And first order perturbation theory, after you work out the details, you end up with this result to where you could say that the fraction of molecules not bonded at the set of sites alpha is equal to the product of the fraction of molecules not bonded at the site A, where all those sites A are in alpha. And it's this partitioning which allows for the simple, elegant TPT1 solution. There's been quite a bit of work over the years in comparing TPT1 to monomer fractions, and I'm not going to go into detail about that. But what I want to point out here is that is that while you can get good representation of a monomer fraction, that doesn't necessarily mean that you're going to get good representation of the entire hydrogen bond spectrum. Fowle et al. Applied polar PC staff with the TPT1 association to alcohols and performed molecular simulations to calculate the hydrogen bonding structure in the liquid. And this is what we're showing here. So this is hydrogen bonding in liquid ethanol at 298 Kelvin. This is the fraction of molecules which are bonded 0, 1, 2, or 3 times. And this is the number of hydrogen bonds. Here the blue are the molecular simulation results, and the red are the TPT1 predictions, where the TPT1 itself was parameterized to VLE data. What you can see is that the fraction of molecules which are bonded twice here is substantially overpredicted, or substantially underpredicted by the theory. And then the fraction of molecules bonded 3 times here is substantially overpredicted. So fraction bonded twice underpredicted, fraction bonded 3 times overpredicted. And this is consistent with the fact that TPT1 does not account for steric hindrance between sites. Because if these are not sterically hindered, it would be easier to bond for the molecule to become fully bonded. Now, the lack of steric hindrance, this results in the overprediction of the fully bonded state, but this is not a parameterization issue. TPT1 is completely incapable of reproducing this distribution because it has forced on it this partitioning assumption, where we say that the fraction of molecules not bonded at the set of sites alpha is equal to this product. But then once you're giving an XA, then that fits the recipe hydrogen bonding distribution. So what we wanted to do was to work out a second order theory for alcohols to see if we get a better agreement with this hydrogen bonding distribution. We did that. We developed a second order approach. Now, second order approaches are much more complicated than the first order approach, but what we've shown is that you can obtain good general second order solution to Wertheim's perturbation theory for an arbitrary number of components where every molecule can have an arbitrary number and type of hydrogen bonding sites. But with the second order term, if you just allow for 2 sites on a molecule to interact with each other in a second order way, you can still obtain that general solution. So in our alcohol solution, we pick those 2 sites as the 2 oxygen sites on the ethanol, where we allow those sites sterically hinder each other. Within TPT2 then, this partition relation no longer holds. And also within TPT2, you end up with an additional geometric parameter, this psi, where psi is equal to the probability of non-overlap of molecules 2 and 3 when they are both hydrogen bonded to the oxygen on molecule 1. So for psi is equal to 1, that means the probability of overlap when 2 molecules are hydrogen bonded to another molecule, that means that the probability of non-overlap is 1, and that is in fact your first order limit. In TPT2 then, in addition to the standard unbonded fractions, the XAs, you also end up with an additional fraction, which is the fraction of molecules not bonded at either site, O1 or O2, and this is this XOO, and we can actually obtain analytical solutions for this in terms of psi and the fraction of molecules not bonded at a single oxygen site, XO. We apply this to ethanol here. We incorporated this TPT2 hydrogen bonding theory within the simplified PC-Saft equation of state, and we adjusted the model parameters to vapor pressure, liquid density, and heat vaporization data. These are the parameters. As you can see, the psi obtained. So this is the non-overlap probability is 0.2, which represents a very significant steric effect between the 2 oxygen sites. These are the average deviations for vapor pressure, liquid density, and heat of vaporization. Overall, you can see the second order effect gives a better correlation than the first order, or second order theory gives a better correlation than the first order theory, but the more interesting part is actually the hydrogen bonding structure predictions. So we're going back to compare to Fowle et al.'s data. And again, these are the fraction of molecules. Here, the blue ones are the simulations, and now the green ones are the TPT2 results, and the red ones are the TPT1 results. So you can see that TPT2 gives a much better description of the hydrogen bond spectrum of this data than TPT1. And I remind you that you cannot get these results with TPT1 by reparameterization. It's simply not possible. Then we wanted to apply this new approach to water ethanol data, but to do that, we first had to have a water model which gave accurate water hydrogen bonding predictions. There's been a lot of a lot of work in the literature and applying SAP models with a 4C approach to acceptor and to donor sites to reproduce lux data with mixed success. What we did is we applied this 4C water model. We fit it to vapor pressure and liquid density data as well as lux data, but we only did so over a limited temperature range, so between 293 and 473 Kelvin. We chose this temperature range because within this range, we could get a good representation of the vapor pressure, the liquid density, and the fraction of unbonded sites. So while this wouldn't provide a good general purpose water model because it's not going to be accurate at higher temperatures, for the purposes of this comparison, it's good enough. We also had binary interaction parameters between water and ethanol, and those were fit to binary VLE data. These are the results of hydrogen bonding, ethanol hydrogen bonding in aqueous mixtures. Followed it all again. They perform molecular simulations to measure the average number of hydrogen bonds. This is NH8B of ethanol in these aqueous mixtures, and these are versus mole fraction of ethanol at two temperatures, 298 and 373. We've normalized these results by the average number of hydrogen bonds in pure ethanol, just so we can see the compositional dependence. You know, the symbols of the data, the dash curve is TBT1 and the solid curve is TBT2. You can see that TBT2 gives a much better representation of this data than TBT1 does. So we were able to show that TBT1 yields hydrogen bonding distributions for ethanol, which are inconsistent with molecular simulation data. We believe this is due to not accounting for steric hindrance in the TBT1 approach. We developed a TBT2 theory, which does account for the steric hindrance between the two oxygen sites on an alcohol. The general methodology we've developed, you can see in the external manuscript, was developed for arbitrary multi-component fluids where each species can have an arbitrary number of association sites, but there is a limit that each species can exhibit at most 1 second order interaction. It was demonstrated that this new TBT2 theory gave hydrogen bond distributions consistent with molecular simulation. You know, the question at the end of the day is, does all this extra physics result in a substantially more capable engineering equation of state? That remains to be determined. A lot of times with the SAP approaches, smart parameterization can fit out weaknesses in the theory. So it'll be interesting to see if this extra physics can really be exploited in the deployment of an engineering equation of state. These are my references. Thank you very much for listening to my presentation.